Okay, so the first one was induction. We had to prove that 1 squared plus 2 squared all the way up to n squared equals this. For all positive integers, n for all positive integers. All right, so does it work for the base case? Well, yes. So for n equal to 1, I'm skipping a bit of the writing here. It's standard. I can give you that exactly if you want at another stage. But at n equal to 1, we know that works because 1, I'm taking the right hand side here. 1 plus 1 plus 1 plus 2 1s plus 1 all over 6. And I'm sure you did this. It gives you 6 over 6, which is 1. And then we know that on the left-hand side, 1 squared is 1, so it holds. So, okay. So then I'll write out the assumption. I assume this is probably more induction. Inductive hypothesis, it's called. 1 squared plus 2 squared, etc., etc. You know all this. K squared equals k. K plus 1, 2k plus 1 over 6. All right, so you know all that. And then we're going to do the inductive step. So we're going to prove it. It's not a tape. We're going to prove it. So we're going to show that it holds for all p is n is equal to k plus 1. So we're going to replace the k plus 1. So once again, this is more for if you're watching this in revision and you've totally forgotten how to do it. You just replace all k's with k plus 1. So that goes to k plus 1, that goes to k plus 2, and this goes to 2k plus 3, I think, because the 2k is doubled. So that is often a mistake in this question. Right, so we have over 6. So this is the thing we need to prove. So I'm going to work on the left-hand side. So my idea, Tamara, is to get this to look like this, because I can substitute in this into it. So I substitute the assume into the proof part. So what this is really is I could put in, there's also there's a k squared there, isn't there? If I keep adding up to k plus 1 squared, there's a k squared there as well. And that means this bit I already have an assumed term for, and that's this bit. So you will always have to use the inductive hypothesis at some stage in the proof. You'll have to use the assumption at some stage in the proof, and then you say from assumption step or from the inductive hypothesis step. So I'm going to replace this bit with this bit because that's allowed. K plus 1 and 2k plus 1 all over 6 plus k plus 1 squared. Okay, so that's another way of writing this, and I haven't broken any rules, and that is that's fine. Now I have to get this to look like what I'm trying to prove, and that's just, I suppose, more algebraic manipulation at this stage. All right, so I decided the first thing I would do was get a common denominator of 6. So that means that'll be it's going to be all over 6. So it's going to be 6 times this, and that's now going to be all over 6. And then so I want to make it look like this. So anytime you can kind of start to make it look like this, you should go ahead and do that. So what I'm going to do is, I've noticed that k plus 1 is here and here. and it's out the front of the thing I wanted it to look like. So I'm going to put it out the front, so I can factorize that bit out. Right. Now, no, I don't quite have the rest. I do have a potential 2k here, but it's not plus 3. So what I'm going to do is I'm just going to multiply out what's remaining. So k times this 2k plus 1 needs to be multiplied out. I factored out the k plus 1, but I haven't dealt with these two. So put those together. That's 2k squared plus k. So this might be a trial and error. I might be going down the wrong path. I know I'm going down the right path here, but sometimes you need to go back and maybe usually factorizing is the key to these to pull out stuff that looks like this. But we'll see how it goes for me. So I've done that, and then I'm gonna, one of the k plus 1s here is gone, so I have 6k and I have plus 6. Okay, and that can be tidied down. That's actually, well, 7k, so I won't rewrite that in another line. So I have 2k squared, so that's a quadratic. 2k squared, 7k. So I'm going to factorize that quadratic. And I want to get it to look like this. So I'm going to put this k in the bracket, the 2k down here. Still all over 6. Now, will this work out? Factors of 6 are 2 and 3. And I think that's going to work out to be correct to match this, because I want to make 7k. I think if they're both plus, I get a 4k and a 3k. So I make my 7k. That is it. That is it done. And then you say your hence p holds or whatever for all k greater than equal to 1, and go on. N equal to k holds, n equals to 1 holds. If they all hold, it's true. But hopefully you follow that tomorrow. That wasn't too bad. So this would probably be a straightforward example if this came in an exam. All right. So, Sean, did you do it the same way as me?
No, I didn't realize that there was k plus 1 on both sides, so I just expanded both sides and said left-hand side is right-hand side.
Oh, so you expanded this as well?
Yep.
I'm like, oh, okay, so you had a real cubic equation on both sides. Okay, yeah. Yep, that's fine. As long as you have left-hand side equals right-hand side some way. Yeah, I didn't touch the right-hand side, so. Yep, there's more than one ways to do it. All right, so the second one. Was show, okay, so this one, Tamara, did you get this one okay? The second one? All right, I'm not too sure from there. No, keep working. So what I'm going to do is I'm going to cube these out separately and then add them together, and hopefully, so I use binomial expansion here. So 8n cubed minus 12n squared plus 6n minus 1 cubed plus 12n squared plus 6n plus 1. And I expand them out, and I can do that the slow way, but that was done through binomial and Pascal's triangle and stuff. And then I add them together. So these two are going to cancel, and we're going to be left with 16n cubed plus 12n. Right, so that's show that. You have shown that. And in part B then, hence or otherwise, prove the sum of two cubes of any two consecutive odd integers is divisible by 4. So they kind of set this up for you. In general, 2n is always even. Very happy with that.
Yes.
And then if I, therefore 2n minus 1 is odd, and 2n plus 1 would be the next odd number, wouldn't they? Odd and odd, and this they would be consecutive. Oh, did I spell that right? I'm not sure, it doesn't matter. So they're two consecutive odd numbers. Right, so that means it is this thing. what they have to prove, hence where the prove the sum of the two is always divisible by 4. All right, so cube them both. We've done it. This is our solution. Is this divisible by 4? Well, of course it is, because we can factor out 4 out of it. You can actually factor out 4. Is it just 4? Yeah, you can just factor out 4. You can factor out 4n if you want. But 4n cubed plus 3n is inside, so that's it. There you go. That was quite simple, direct proof, that one. Right. Question 3. Proof by contradiction. Okay. So we are asked to, prove, not assume, that root 3 is irrational. Okay. By contradiction. So, I mightn't use your method, Sean, but what was your method?
I said we have two integers, a and b, and we can, if it is rational, then we can write root 3 as a over b, and we assume that a and b have no common factors.
Yeah. Okay. Yeah, that's exactly how you do it. Assume that root 3 is rational, because if it's contradiction, you have to go this way. Is rational. In other words, it can be written as a fraction, which Sean rightly says, a over b, and this has to be in its, and we're also assuming that this is in its slowest terms. In other words, assume a and b have no common factors. Okay, so it has already been fully simplified. What do you do next, Sean?
Then I squared both sides, said 3 is equal to a squared over b squared.
Okay.
Then multiplied out by b, said a squared equals 3b.
A squared equals 3b squared. Therefore,
a must be a multiple of 3. So a can be written as 3k. Well, a squared is a multiple of 3, which means a must be a multiple of 3.
Yeah, so I said divisible, but yeah, it doesn't really matter. A squared is divisible by 3, therefore a itself is divisible by 3, which hopefully makes sense. Therefore, you can write
a equals 3k, I said.
Yeah, I'll use k as well. For some positive integer p. Okay, no, you use k. All right, so therefore you can then replace your a with, well, yeah, that's what you did. A, so instead of having a squared equals 3b squared, you now have 3k squared equals 3b squared. So you have something like 3b squared equals 3k squared.
Yep.
And that's 9k squared then is equal to 3b squared. And this is where the contradiction starts to come, doesn't it?
Which means that, yeah, because it means that b squared is equal to 3k squared, which means that b squared must be divisible by 3, which means that b must be divisible by 3. But we said before that they can't have any common factors.
Yeah. So b squared is also divisible by 3, and b, therefore, b is divisible by 3. This is a contradiction. As a and b have no common factors, which we said at the start. So therefore, our original assumption is false, and by proof by contradiction, root 3 must be irrational. Did you remember how to do that, or did you look it up again? Or
looked it in the book.
Yeah, so it's in the book, that example, or a very similar example. So you do the same for root 2, whatever you need to prove something is irrational, go down this road. All right, so that's question 3. So that's one you'll have to remember. It is obvious when you look at it, but perhaps not obvious exactly how you do it when you start it. All right, so question 4 is back to our proof by induction. This was not easy.
Yeah, it wasn't. The induction part, but it took me a while to figure out.
Yeah, it was. This is be a hard one, yeah. Okay. Tamara, you still there?
Yes.
Okay. Any questions so far?
No.
So that proof by contradiction example is in that book 2. It's in whatever chapter 9 or 10. I can't remember which. Okay, if you want to check it out again, or you just rewatch this video. Okay, so the next one was difficult. It looked easy, but then got difficult. Prove that. So question 4 was prove that n squared plus 5 is divisible by 6 for all n integers greater than 1. Okay, so let's just set it up. Make sure it works for the base case or test or whatever you want to say. So this is our test to start off with. N equal to 1. Well, does it work? 1 times 1 squared plus 5, and that is then 6, which of course is divisible. So it works. So I'll do the inductive hypothesis. Assume n equal to k is true. So I got k times k squared plus 5 is equal to, is divisible by 6, not equal to 6, divisible by 6. Okay, and now we'll get going with the fun stuff. Inductive step, or the proof. Okay, I will. All right, so my first thing, I'm going to replace this with k plus 1. So it'll be k plus 1 times k plus 1 squared plus 5. And we're going to try and prove that that's divisible by 6. So the key anytime you're trying to get divisible by something, this type of question, is to get it to be factor out 6 out of it somehow. So
Yes.
a bit like the question 2, but question 2 is far simpler. To prove that this was divisible by 4, just have to factor out 4 out of it, and then, oh, yay. But this, at the moment, does not look like it's going to be divisible by 6. But Sean is going to tell us how to make it divisible by 6, isn't Sean?
Well, I did step 2 differently, actually. I said the assume n equals k. I said that is equal to 6p for some integer p.
Oh, you said that this is, yeah, okay. You said that 6p equals 6p?
Yeah.
Okay, yeah. I think this is the way when we did this before, that's the way I did it. I did it a different way this time, but yeah.
Okay, and then, what did I do next? Oh, and then for some reason I split it up, but that's, just to make it easier to read, I split it up into 2 parts. So k times the stuff on the right plus 1 times the stuff on the right. Yeah. And then inside of the first set of brackets where we have k plus 1 squared, I said k squared, I said that expands to k squared plus 5 plus 2k plus 1.
Like that?
Yeah, and then on the right side, I just expanded it like normal.
What's it, just simplified k squared?
Simplified to k squared plus 2k plus 6.
Thank you. Okay.
Okay, and then from the first set of brackets, I broke it up into the k times the k squared plus 5, and then I substituted in 6p. So it was k times k squared plus 5 plus k times 2k plus 1, and then plus all the other stuff.
Yeah, so that's still there. So this is the bit from the inductive hypothesis. We can say that's 6p.
Yep.
So you can. Okay, so that's definitely divisible by 6. Yeah.
And then when everything else is expanded out, it becomes 6p plus 3k squared plus 3k plus 6.
Okay, so all this expanded and simplified down gives that.
Yep.
Yeah.
And then I factorized out 3k from the 3k squared plus 3k. And then I factorized out 3 from everything.
You divide it. Oh, okay, out front here.
Yeah.
You need 2p. Yeah?
Yeah, I wrote it as 2p plus 2, then plus the k, just to make it clearer.
Yeah. Plus k times k plus 1 like that.
Yeah. And then I said, since k, so 2p plus 2 is always going to be even, and k times k plus 1 is also going to be even, because if k is an odd number, then it's an odd time. No, then it's an odd times even, which is even, and if it's even, it's just even. Yeah, it's always going to be even. So that means the inside is always going to be even, and an even number times 3 is always divisible by 6. So it's been pretty.
Yeah, so that's, if one is odd, the other has to be even. So an even times an odd is always even.
Yeah.
So they're both even, which means this whole thing you're saying is divisible by 2?
Yes, which means that the whole thing, if it's divisible by 2 and it's being multiplied by 3, must be divisible by 6.
I don't know what you say. Hence, it all is divisible by 6.
Yeah.
Hence, it all. No, hence. Right, 6. Yeah. Yep. Yeah, we did this before in class, and I did it that way.
Well, how did you do it this time?
Yeah, I know. I kind of forgot that way, and I did it a different way. I did it. I'll just. Maybe I'll do it on a different page. Will it fit? Might not fit. I'll do it on a different page. So all the same stuff. So I was just saying divisible, but I did use the same kind of finish as you. I don't think it was just the same finish. I did use the fact that either k or k plus 1 must be even. I don't think it's actually necessary for me to go through it. I just isolated k times k squared plus 5, and then I ignored that then because it is divisible by 6. And
yeah.
Then I focused on. I did some factorization. I had 3k squared plus 3k plus 6 as well.
Yeah.
I did some sort of same manipulation because if I factor out the 3 out of that, I'm left with k squared plus k plus 2, which is 3 times k plus 1 plus 2. And this is where I said odd even. So that's even.
Okay.
And plus 2 is then definitely going to be even. So therefore it's very similar. But yeah. So you have to almost generate to be divisible by 6 there, because it's not initially obvious to factor out 6, which was definitely a problem there. So you had to generate, which is the odd even thing, which can come in the odd time into these proof by inductions. All right. Yeah, not easy, but hopefully it's making more sense now tomorrow, the finishy bits. So these are kind of the 3 different styles that can be asked. I
find it strange that that's only worth 6 points. It's not very nice.
No, I know, yeah, but that'll be question 6 or 7. The way I've heard this before, but it gets easier. No, it starts easy and then gets harder towards the end of the short questions, and the same then for the long one. Yes, proof by induction is going to be either some series, usually some series like the first one, or some divisible like 4, or some derivative, like question 5, what we're going to do now. So if you do all 3 of these, I think you're fairly. Now, it might. Yeah, that's pretty much the only 3 they ask. Okay. This I didn't think this was easy either, by any means. Okay, so we have this function, which is going to find the first derivative. So that shouldn't be too bad. Did you get to do this one tomorrow, or did you kind of not get that far? So I'm going to use the product rule. I didn't hear that response if there was one. Minus, so it's the derivative of this is 1 times that, and the derivative of this times this then is going to be minus 2 in front, x plus 1, slightly rearranged e to the minus 2x. So hopefully that was no issue. Now, I did factorize here, noticing what's coming up. So I just took out e to the minus 2x, and I put it at the end because that's the way in part B they are setting it up. So I did 1 minus 2x plus 1. You didn't have to do this. This is just me seeing what's coming up. And you can put in, and that's e to the minus 2x. So just factor out that, but this is fine. Okay, so part B then asks for a proof by induction. Prove that I suppose the general derivative of this will be that long thing that I'm sure you've written. So I'll write it when I get to the k step. So let's just make sure it works for n equals to 1. So I have that from this part already. So if it works for n equal to 1, we're good because we know that the first derivative is this. So I want to prove that it works for n equal to 1. So that's going to be d1f dx1. So this was written in the question, the actual formula for this. I'm not going to write it out yet. So I'm just replacing n with 1. So that's going to be 1 minus 2 times 1 minus 1 plus minus 2 to the 1 x plus 1 e to the minus 2x. Perhaps I actually will put in the thing because this is looking good. So what it gave us was this. That's a general expression. Okay, so that was the general form, and then once I sub in 1, so I have to get it to look like this, and I think it does. When I do all this out, minus 2 to the power of 0 is going to be 1. 1 times 1 is 1, which is good. I want that, so that's 1. And then minus 2 to 1 is minus 2, so that makes the minus 2 we want. And that's x plus 1. And then that's e to the minus 2x. All right, so next part then, so that's n equal to 1, so that's test. We're now going to assume, and for n equal to k, so I'll write it out, dkf and dk, oh, it is x and f, isn't it? That's weird. Is, just replace k up here, so apologies if this is boring, k minus 1 plus minus 2 times k, x plus 1, and then e to the minus 2x. Okay, now comes the fun. So for the inductive step, I'm trying to prove this holds for n equals to k plus 1. So let's do the k plus 1 bit first. So that's k plus 1 f dx k plus 1. So for any derivative, it will follow this formula. I'm just going to keep replacing k plus 1 minus 2. That was k minus 1. Adding 1 is just going to make it k. That k becomes k plus 1, and then we have x plus 1. e to the minus 2x. All right. All right, so we gotta make this or use this at some stage and try and get this. I'll ask you, Sean, how you went about this.
I said that dk plus 1 whatever is equal to the derivative of that, then I derive the dk one.
Okay, so you derive this.
And then I show that it's equal to that.
All right, so let's derive this whole thing. So we got to use this step. So we're going to derive this here. Okay, so we're going to derive that. The derivative of the left side here is dk plus 1 dx k plus 1, isn't it? So it'll be the next derivative. The derivative of this side, I think it's a product rule. That's one bit, and that's another bit. I'm going to use product rule. So the derivative of this bit, well, I think this is a constant, so it goes away. And the derivative of the x bit is 1. So that's just 1. And that's just going to be multiplied by this minus 2k. So minus 2 to the k. So that's that minus 2 to the k times 1 is the derivative of the inside bit. And then that's just going to be multiplied by that because of the product rule. E to the minus 2.
Isn't the k on the outside of the bracket, sir?
K on the outside of the bracket. Oh yes. Sorry, good call. I was confused. Yeah, sorry. That's. Yep, not like that. Okay, so that is the derivative of the first times the second. Now we got to do the derivative of the second times the first. So, so derivative of e to the 2x is going to be, well, that's chain rule, minus 2 times this. I'm going to put the minus 2 in front because no point putting plus minus. I'm just going to put minus 2 in front. And then I'm going to put everything that's there already. So all this term comes back in. It's minus 2x. All right. Hopefully you followed that tomorrow. I don't know if you're still there. At this stage, I factored out this to the end because that's what we're trying to make it to look like this now. So it has this at the end. So I'll do that first. So minus 2 to the k is still there. As I did this, I multiplied in this minus 2 as well. So I get minus 2k minus 2 to the k plus 1. And I get another minus 2 times this one, minus 2k x plus 1. And then that's all factored out. So I did two things at once there. I multiplied in by these two terms, and I factored out this. Right, it's getting closer. So once again, if I get it to look like this, I have done it. I've proved it. So I need a k plus 1. Right. Let's just look at these two. So I could rewrite this. I'm just going to take a little sidebar over here. That's minus 2 to the k still. It's from there. And I can call that, because that's minus 2 to the 1, really. And that's minus 2 to the k plus 1.
Shouldn't it be k minus 1?
Yes, I've taken that down wrong. I knew I was going to go to k plus 2. That would have been not right. So, yes, thank you, Sean. So that's k minus 1 from here. I just took it down wrong. So that's 2 to the 1, minus 2 to the 1, and then so these two would if you just had that as your problem, you would add the powers and you'd be left with -2 just to the k. So just left with this k here in front of it, and it's -2 to the k. Hopefully that made sense to you, Tamara. Okay, so that was this term. All right, and there's a k there as well, so I can just put the k was there in front. All right, so I'm going to replace that, but also this can, you can then factor out a 1 out of this and a k out of that to make, so I'm just trying to force out a k plus 1 really. So I do get a k plus 1 when I factor that out. And what's left behind is -2 to the power of k. So that was a little sidebar, and I'm going to put that back in. K plus 1 times -2 to the k. Sweet. Now, I got to make what's left over here. This bit look like this. And for the same reason, these two -2s, that's -2 to the 1, and that's -2 to the k, so they will combine to be -2 to the k plus 1, won't they? Okay, so I have that bit. X plus 1 is still multiplied, and I'm home. Okay, so I just by deriving this step, prove that in general, the next derivative of the previous one will always be this, which is what I wanted. So it's proved. Okay, so that matches something like this. All right. Now this question continues, and we need to find, so this is all without a calculator, we want to find the coordinates of the local minimum and maximum points on the graph, and justify whether the point is a max or a min. Okay? So Sean,
Yes.
what'd you get as your max or min?
I got x equals -2 as the x value, and then I would just substitute that into the first equation, so it's a half of e to the 4 for the y value. And then I justified that it was a maximum using the second derivative by substituting it in, and it was...
What was your method for it? You got it wrong.
I did?
I think so. Well, you didn't get the same. It's possible I got it wrong, but...
I said 0 is equal to the first derivative.
Okay, yeah, so if you want to find a...
My graph was the right shape when I checked later, though. I guess it's just at the wrong point.
Possibly. I thought mine has the right shape too, but sure, we'll see. That's... So the first derivative we had in part A, didn't we? And that's 2 to the x plus 1 is equal to e to the -2x equals 0. Okay, so that's factors. So that's... you can use the null product rule. So that and that can be let equal to 0, can't they?
Yep, but e to the -2x can't be 0, so...
No, it can't, yeah. Okay, so that means that just this part can be equal to 0. Now I got -1/2.
That's what I said.
I just said minus, you said 2.
I said 1/2.
Oh. That's the same as me.
Okay.
Did you get minus or positive?
Minus.
Oh, okay. You did get it. Okay, so solving this is equal to minus. Just heard the 2. All right, and then you can either use, well, you could use the second derivative, yes, of course, or you could use this first derivative and just sub in, can't you? Just to see if it's increasing or decreasing before and after this point.
Yeah, that works too.
Yeah, so I just subbed in a large value and a small value and saw that, up to, so from -infinity up to 0.5, you get positive values, and from -0.5 up to infinity, you get negative values. This using the first derivative, which suggests that the function itself is increasing because its slopes are increasing there and it's decreasing after that. So therefore it's a max. You can do it your way as well. So it's a local max at minus 0.5. We'd say that for sure. And then if you sub it in to the original thing, you'll get a value for E as well. And that's, you got a half E, yeah?
A half E, but E to the 4, right?
No.
No?
Well, let's see.
Oh, no, E to the 1. Yeah, no, that's when I multiplied it by 2. That doesn't make sense. It should just be a half E, yeah.
Yeah, half E. Okay, a half E, or you can write it literally as a half E there. Yeah, because it's going to be minus 2 times minus half.
Mm.
All right. So that's our local maximum. Part D then asks for something else. Find the coordinates of any point of inflection. So point of inflection is the second derivative equal to 0. Now the second derivative, intriguingly, is got, of course, we have the formula for it here, don't we?
Yeah.
So if that ever focuses. So we have our formula for it here. That is the second derivative formula, or any subsequent derivative formula. And we can replace, what do we replace? K with 1. Is it? So you get 2. No?
Don't we replace K with or N with 2? Because that would be the second.
Oh, here, yeah, sorry. No, I was using the
Oh, okay.
Apollo, so I was replacing it with 1 because 1 plus 1. Yeah. Or you can use this one, yes, of course. Okay, just straight away with 2. Either one would have worked. You're going to get what did you get for this point?
I got X equals 0.
Yeah, okay. So this is using what we found in the previous page. Just subbing in 2 in Sean's case, or 1 in my case for some reason. I use this. So this bit was the same as before. That bit can't equal 0, so we just ignore that result. This bit, when you try and solve it for 0, you get 0.
Yes.
X equals 0 from that equal to 0, which I won't do. Therefore, there's a point of inflection at 0. Once again, I used. How did you test whether it's concave up or down, or what did you do?
I said I tested -1 and 1, so either side.
Yeah. So once again, from negative infinity up to 0, we can test points in the second derivative, and it's always negative.
We also need to do that to justify that it is a point of inflection, don't we? Because sometimes it's not, even if it's 0.
Yeah, but if it changes from negative to positive.
Yeah.
So if it's negative, it's not. Yeah. So doing this test is the test. So that's concave. CU means concave up and down. Okay, so there's, we've noticed that there is a change in concavity from down to up after 0, or at 0. So therefore it is a point of inflection. So you can make a note of that. There's a, PowerPoint. Change in concavity. So yeah, there is a point. Okay. All right. So you find the corresponding y value, and you put in 0 into the original, and you get 1. I think, is it?
Yep.
And you do that. So put it into the function, do all that. So our 0, 1 is our point.
Yep.
Or the inflection point, and part E then asks you to sketch this. All right, so I don't think we need a massive scale. 1 and 2, so minus 1. I did get the x-intercept before I drew this, and the x-intercept, when you let the original function equals 0, get x plus 1 is equal to 0, so x is equal to -1. So again, that's the x-intercept, which I think is the point you might need. I also tested the limits. I don't know, did you do that, Sean or Tamara?
I didn't, but I just kind of thought about it for a bit, and I thought, okay, if I sub in a higher value of x, it's going to approach 0.
Yes.
Okay.
So yeah, you can do a little bit of work on the limits just to see where it's going to end up. Limits as x approaches infinity and minus infinity. That's not an infinity symbol, that's an 8. But minus infinity and infinity. So as that function, you can just test larger and larger values. As it goes towards negative infinity, I think it goes towards negative. As x goes towards negative infinity, the function goes towards negative infinity itself.
Yeah.
As x tends towards infinity, it's getting really, really small, e to the power of minus 2x. And that's so it's towards 0. So we know it flattens out towards 0. So let's put in all those points we know. The x-intercept is minus 1, 0, so that's here. The y-intercept was 0, 1. We had that before as a point of inflection. Which means it's going to be a little bit of a turn there. We had a maximum as well at minus a half and a half of e, so half of e is going to be somewhere around here.
Yep.
Mated plus. And we know that it will flatten out towards here, and you know it's going to dive down towards infinity as x goes towards infinity. So there's a maximum here, a little change here of inflection, and then it starts to tend down. Perhaps I flatten it out bitterly, but something like that.
Yeah.
And that is our function. Y is equal to x plus 1 e to minus 2x. So a bit of calculus in there as well, just for fun. A lot of calculus in there in the proof by induction question. All right. So well done. Got that one. We're moving on to the last section then of systems of equations. So that's our 3x3 equations, row echelon form and all that. If you have some additional questions from the textbook for proofs, perhaps you haven't got to them yet, but perhaps you can today. Chapter 9 and 10 from the book. Put them in. Questions. And yeah, I'll put up those system of linear equations questions in the next 5 minutes. So if you want to keep checking that. Sean, any questions or anything?
Nope. I think that was pretty good.
All right, so get on to, if you want to look at question 9 and 10, just see if there's anything that's stumping you. And you can put it in there. If not, give me 5 minutes and I'll put up the system of linear equations, and you can look at chapter 11 as well.
Okay.
All right, see you, Sean, tomorrow. You stay on there.
See you, sir. Thank you.